Okay, so welcome back. We're going to do another practical lesson today. We're going to do the conductive putty practical, which you'll find the details of in your notes, page 9 to 11. You're going to be taking measurements. I'm going to carry out the practical, and then you'll need to calculate resistance, so using Ohm's law, and then we'll draw some conclusions from that. Now, first of all, I'll just draw out the circuit diagram we're going to use. You have this diagram in your notes already, so we're just going to go through it quickly. Now we have our ammeter here, and it's placed in series, it's in our circuit, and our voltmeter, of course, is placed across our components. And then this is going to be our conductive putty. This is what we're going to be varying. We're going to be changing its length, and we're going to be changing its cross-sectional area. And then our two cells are going to make up our battery as well. Now, what is conductive putty? Well, it's really just a soft Play-Doh-like material that also conducts electricity. It's good because we can change its dimensions very easily, and we can see what effect this has on its resistance, which is what we're going to be doing today. Now we're going to use a multimeter again as a voltmeter, and I'm going to set this to measure volts. And we've got a second multimeter that we're going to use to measure amps. That's going to be our ammeter. We also have our battery here, made up of two cells. And what I'm going to do here is I'm just going to connect up my circuit. So I'm connecting my ammeter in series in the circuit. Now what I'm doing here is I'm actually placing the wire on the wrong port in the ammeter. I'm going to fix that in a minute. And then I'm going to complete my initial circuit through my conductive putty, through the battery, and through the ammeter. So they're all in series with each other, and that's just like our circuit diagram. And then I'm going to bring in my voltmeter at the end and place it across my conductive putty. Remember, voltmeter is always placed in parallel across the components we are measuring. Now at this point I'm starting to realize that the circuit isn't working. I'm trying to work out what's gone wrong. Here I'm doing a short circuit. You shouldn't ever do this. It's not a good idea. And then that's me realized what's gone wrong, and I've fixed the wire. Again, I shouldn't be doing a short circuit there, but now it's working. Now my circuit's working, and we're ready to start taking some measurements. Okay, so let's start by varying the length of our conductor, and we're going to start with a cylinder of conductive putty that has a roughly uniform diameter, and we're going to measure across the full length of our conductor to start with. So take a reading of the current and the voltage and calculate resistance. Then I'm going to cut this conductor in half, and we're going to do the same again. We're going to measure current and voltage, so take some readings and calculate resistance. And then finally I'm going to cut it in half one more time, and we're going to do the same again. And what we should have now is a set of measurements that show us how the resistance varies with the length of a conductor. Now in this next section we're going to be varying the cross-sectional area of the conductor. So what I've made up here is three separate cylinders, all roughly the same length, but each with a different cross-sectional area. And we're going to start with the largest cross-sectional area, and again we're going to take our readings of voltage and current and use that to calculate resistance. Then for the second conductor with a smaller cross-sectional area, and then finally the smallest cross-sectional area. And what we should have now is a set of results that show us how the resistance varies with the cross-sectional area of our conductor. So the point of this practical is, one, to look at how resistance varies with the dimensions of a conductor, but also to introduce this new quantity called resistivity. Now, resistivity is given the symbol of rho, which is a Greek letter like a curly P, and we define it as the same value as resistance between opposite faces of a cubic meter of material. Now, these should go into your notes. So just like resistance, resistivity is a measure of how much a material opposes the flow of current. But the difference is resistivity is independent of the dimensions of the conductor. So it doesn't matter the shape of the conductor, the resistivity is a constant. So what we can say is, if we look at resistance versus resistivity, resistance varies with the dimensions of a conductor, whereas the resistivity does not. It's constant for a material that's at a fixed temperature. Okay, so moving forward, what I need you to do. One, you need to complete the conclusions on page 12. Then you need to decide on a relationship between resistance and length and area. Then I'd like you to research the formula for resistivity and add that to your notes. And then carry out the resistivity calculations that I will set for you. Okay, thanks.